Section: Introduction. In this section, we discuss our motivation for developing shared attention, SAW, outline our method, and compare it to existing key-value sharing mechanisms. Our motivation stems from the self-attention mechanism used in transformer models, which is typically defined as the softmax of the product of the query and the transpose of the key, divided by the square root of the dimension of the key vectors, multiplied by the value matrix. This process requires us to recalculate attention weights at each layer, which can be quite demanding in terms of computation, especially during inference. To address this, we use a key-value cache to minimize the need to recompute the key and value matrices for tokens we have already encountered. While previous methods have aimed to share key-value caches at different levels to reduce memory usage, they often assume that attention weights vary significantly across layers. This assumption leads to the need for separate computations to capture different contextual dependencies effectively. This raises an important question. Are the attention weights really that different across layers, or is the variation small enough that we could use a unified approach across multiple layers? To investigate this, we conducted an empirical analysis of the attention weights across different layers of the model, specifically using the Llama 2-7B chat model and the Massive Multitask Language Understanding (MMLU) dataset. We extracted the attention matrices for each layer and standardized them to a consistent size by applying zero padding. We then used cosine similarity to compare these matrices across layers. Our findings showed a high degree of similarity among most layers, particularly from the 3rd to the 30th layer. In contrast, the first two layers and the final output layer had much lower similarity scores compared to the middle layers. This makes sense because the early layers are closer to the input embeddings and need to adjust their attention distribution frequently to accurately capture the meanings of diverse inputs. Similarly, the final layer's unique role in predicting the next token justifies its different attention pattern. Based on these observations, we hypothesize that the high similarity in attention weights across most layers allows us to share these weights, which could eliminate the need for separate softmax computations in each layer and reduce the key-value cache size. This strategy could streamline the inference process and significantly improve computational efficiency. Therefore, we propose a novel algorithm called shared attention, which uses a single shared attention matrix across multiple layers. This approach fundamentally changes how we operate by maintaining a consistent attention mechanism across various layers, reducing redundancy and enhancing inference speed. Now, let's compare our method with existing approaches. The original self-attention mechanism in transformers, particularly the multi-head attention model, requires caching the keys and values in each head and layer to speed up inference. This has historically led to significant memory overhead, prompting various innovations to alleviate this burden. Multi-query attention, MQA, and grouped query attention, GQA, consolidate the key-value cache by allowing multiple query heads within the same layer to share a single set of key and value matrices. This effectively reduces the number of unique key and value pairs that need to be stored and retrieved during computation. Cross-layer attention, CLA, takes this a step further by enabling the sharing of key and value matrices across different layers, further decreasing the memory needed for key value storage. However, our method introduces a fundamentally different approach to tackling the challenges of self-attention. While previous methods have focused on minimizing redundancy and storing keys and values, we concentrate on optimizing the computation of the attention weights themselves. In standard practice, cached keys are primarily used to compute attention weights alongside the queries. Instead of facilitating this interaction through shared key-value matrices, our method proposes directly sharing the resulting attention weights, specifically, the softmax normalized scores. This not only reduces memory requirements by eliminating the need to store separate sets of keys for each layer but also significantly lowers computational complexity. By sharing the pre-computed softmax results across layers, we avoid the repeated calculation of softmax, which is often one of the most computationally intensive tasks in the attention mechanism. This efficiency gain translates into a substantial reduction in the number of floating point operations required during model inference, enhancing both the speed and scalability of transformer deployments. Unlike traditional methods that optimize memory use by sharing physical keys and values, our shared attention model innovates on the computational process itself, leveraging the consistent patterns in attention weights to streamline operations across multiple layers of the transformer architecture. Section Summary. In this section, we introduce our novel shared attention (SA) method, which significantly reduces the computational and memory overhead during inference for large language models by directly sharing pre-computed attention weights across multiple layers. Our empirical analysis reveals a high degree of similarity in attention weights across most layers, suggesting that this shared approach can streamline the inference process and eliminate the need for repeated softmax computations. By focusing on optimizing the computation of attention weights rather than just the storage of keys and values, we enhance both the efficiency and scalability of transformer models. Section: Isotropic Attention Distribution. In this section, we analyze the attention weights specific to different layers across various large language models, LLMs, including Llama 2-7B Chat, Llama 3-8B Instruct, Llama 3-70B Instruct, Baichuan 2-7B Chat, Qwen 2-7B Instruct, and Qwen 2-72B Instruct. We evaluated these models using the MMLU benchmark. Our findings indicate a self-organizing pattern in the attention weights across these models. As shown in our figures, there is a consistent global similarity in the attention weights of the layers across all models we tested. This suggests a fundamental structural characteristic in how LLMs process information, which we can categorize into 4 distinct groups. Group 1 consists of the first 2 layers, which are closest to the input tokens and focus on extracting semantic information at the token level. These layers show attention patterns that depend on the data, which are essential for the initial processing of inputs. Group 2 includes the layers right after Group 1, extending up to the 5th layer. The attention weights in this group show high internal similarity but differ significantly from those in other groups. These layers likely act as transitional areas where intermediate semantic features are refined. Group 3 includes the layers following Group 2 and goes up to the second to last layer. This is the largest group in terms of both the number of layers and their function within the model. The layers in this group exhibit a high degree of similarity, indicating a uniformity in the attention mechanism, where refined features are consistently used to enhance the model's understanding of context. Group 4 is the final group, consisting only of the output layer. This layer processes the combined contextual information to produce outputs. Its attention weights are distinct from those in other layers, highlighting its specialized role in making final decisions. The different attention weight patterns we identified across these groups emphasize the idea of functional specialization within LLMs. This categorization not only showcases the varied roles of different layers in processing inputs but also supports the potential for optimizing computational strategies, such as our proposed shared attention method, by leveraging these inherent patterns to minimize computational redundancy. To further understand how attention weight patterns form and evolve during the pre-training phase of LLMs, we examined intermediate checkpoints of the Baichuan 7B model provided by the developers. These checkpoints, which range from processing 0.2 trillion to 2.6 trillion tokens, allow us to observe how attention mechanisms shift as the model is exposed to more data. We used a consistent metric to measure the similarity of attention weights across layers at each checkpoint. We also included the final chat model, which was fine-tuned to align with human responses, to compare the evolution of attention patterns against practical outcomes. The dynamics of these attention weights are illustrated in our figures, showing how attention patterns across the model's layers differentiate and stabilize over time. At the early pre-training stage, with 0.2 trillion tokens processed, groups 1 and 2 appear merged, indicating a less distinct processing strategy in these initial layers. This suggests that early in training, the model does not clearly separate token-level semantic processing from intermediate refinement. However, as the model progresses to 1.0 trillion tokens, we observe a clear division between groups 1 and 2. This separation indicates that the model is beginning to develop more specialized and efficient strategies for managing different types of information. The similarity within Group 3, which includes most of the model's layers, improves significantly, with a similarity score rising from 0.8 to 0.9. This increase reflects the stabilization of the model's attention mechanism and its consistency in processing contextual information. The advancements we see across the pre-training checkpoints not only highlight significant changes in the model's attention mechanisms but also correlate positively with performance improvements on various benchmarks. This includes enhancements in the MMLU, CMMLU, and C-eval 5-shot accuracy tests, which improved from a baseline accuracy of 0.25 to 0.50. This notable improvement underscores the connection between refining attention mechanisms in LLMs and their enhanced capabilities in understanding natural language tasks. Additionally, our further examination of the model's development, as detailed in supplementary material, shows that the similarity within Group 3 continues to improve even after the alignment stage. This suggests that the alignment process, which aims to fine-tune the model to better reflect human-like understanding and response generation, also plays a role in stabilizing the model's attention mechanisms. Section Summary. In this section, we analyze the attention dynamics of various large language models, LLMs, and identify a self-organizing pattern in their attention weights, which can be categorized into 4 functional groups based on their roles in processing information. Our findings reveal that as the models undergo pre-training, the attention mechanisms evolve from a less differentiated strategy to a more specialized and efficient approach, correlating with significant performance improvements on benchmarks. This evolution highlights the importance of attention weight patterns in enhancing the model's capabilities in natural language understanding tasks. Section: Experiments and Discussion. In this section, we present our experiments and discussions aimed at validating the effectiveness of our proposed shared attention (SAW) method. We carried out a series of experiments to test how robust SAW is under different configurations and to evaluate its performance on well-known benchmarks. Initially, we applied the SAW mechanism directly to advanced large language models, LLMs, without any prior training. This was done to see how SAW would affect pre-trained models right away. Our goal was to understand the immediate impact of integrating SAW into existing model architectures. We assessed the performance of these models on standard LLM benchmarks, including GLUE for general tasks, GSM-8K for arithmetic, HELA-SWAG for reasoning, and MMLU for knowledge. As we expected, applying SAW directly led to a decrease in accuracy on some benchmarks. This result aligns with our predictions since we did not retrain the models to fully adapt to the nuances of the shared attention mechanism. Due to limitations in computational resources, we found it impractical to pre-train an LLM from scratch with SAW included. To further explore the capabilities of SAW during training, we fine-tuned base LLMs that were equipped with shared attention using the publicly available Instruct dataset. After fine-tuning, we tested these models against the same benchmarks to observe any changes in performance. This approach allowed us to measure how well SAW could adapt when models were trained to accommodate its dynamics. Collectively, these experiments demonstrate the potential of shared attention to modify the traditional attention mechanism in LLMs, suggesting a promising path for reducing computational demands while maintaining or even enhancing model performance in some cases. We provide detailed results and further discussions on each benchmark and dataset in the following sections. For our fine-tuning experiments, we utilized the Llama 2-7B and Llama 3-8B base models. These experiments were conducted on a powerful hardware setup that included 2 NVIDIA A180GB GPUs. We optimized the models using the AtomW optimizer, starting with a learning rate of 2 × 10⁻⁻⁵. We used the BF16 data type for model parameters, which improves numeric range and stability during backpropagation, crucial for maintaining precision in training large models. Each GPU managed a micro batch size of 16, and we employed gradient accumulation techniques to handle the computational load effectively. Additionally, We used Deep Speed 0 Stage 3 to optimize the distribution of model and optimizer parameters and improve memory management across the GPUs, ensuring efficient resource use. The fine-tuning process lasted for 2 epochs and followed the standard Alpaca instruction format, which is designed to enhance the model's responsiveness and accuracy in handling instruction-based tasks. We tested the application of SAW across different segments of layers within the Llama 2 to 7B and Llama 3 to 8B models, each consisting of 32 layers. To evaluate the robustness and adaptability of SAW, we implemented it in various layer segments, ranging from narrower spans of 4 layers to broader spans of 8 layers. Our preliminary assessments of SA in the earlier layers of Llama 2 to 7B showed a significant increase in perplexity, indicating major disruptions in the model's ability to accurately predict the next tokens. This finding highlights the critical role that attention score variances play in the model's early processing stages, which are essential for setting initial context and extracting features. To quantitatively assess the impact of attention variance throughout the model, we conducted a detailed variance analysis. We used the same computational method to calculate the variance of attention weights in Llama 2 to 7B and Llama 3 to 8B while processing the MMLU dataset. We also explored how attention variance might influence downstream layers by computing a weighted cumulative variance, which aggregates the variances of all downstream layers starting from each specific layer, weighted by the average of these summed variances. Our analysis revealed that early layers exhibited significantly higher weighted variances compared to later layers, suggesting that attention mechanisms stabilize as we move through the model's architecture. Given these results, we primarily focused on applying SAW in the latter layers, where variances appeared to stabilize. The outcomes of these experiments revealed interesting patterns. For the Llama 2 to 7B model, implementing SAW in the latter layers maintained relatively stable performance across various benchmarks, including GLUE and MMLU. However, extending SAW to include more layers, especially mid-level layers, led to noticeable performance drops in tasks requiring mathematical reasoning, such as GSM-8K. In contrast, the Llama 3 to 8B model, which showed higher layer-wise attention similarity, experienced less performance degradation when SAW was applied. After implementing SAW in the layers closer to the model's output, the Llama 3 to 8B even outperformed its original configuration on the GLUE benchmark. This suggests that strategically placing SAW can potentially enhance the model's performance in complex natural language understanding tasks. Section Summary. In this section, we validated our shared attention SAW method through a series of experiments on advanced LLMs, assessing its impact on performance across various benchmarks without prior training. Our findings indicated that while direct application of SAW sometimes reduced accuracy, fine-tuning models with SAW showed promising adaptability and potential performance enhancements, particularly when applied strategically in the latter layers. We also conducted a detailed variance analysis of attention scores, revealing that early layers exhibited higher variances, which informed our focus on implementing SAW in more stable, later layers for optimal results. Section: Fine-tuning on Instruct dataset. In this section, we discuss our approach to fine-tuning existing large language models, LLMs, using the Instruct dataset. Due to the computational limitations that prevent us from training LLMs with shared attention, SAW, from the ground up, we decided to fine-tune models instead. Our goal was to see if this fine-tuning could improve the performance issues we noticed when applying SAW directly. We specifically chose the Instruct dataset because it tests models on tasks that require following complex instructions, which helps us evaluate how well the models can use what they have learned. The results we obtained show a smaller performance gap between the original models and those enhanced with SAW. For example, while the original Llama 2 to 7B model performed better than the version with SAW in direct tests, the fine-tuned version of Llama 2 to 7B with SAW showed notable improvements across various metrics. This indicates that fine-tuning helps the model better incorporate the shared attention mechanism, recovering some of the performance that was lost during the initial application of SAW. Our findings suggest that fine-tuning is a promising method for integrating new architectural features like SAW into existing models. The improvement in performance shows that with sufficient training, the initial drawbacks of applying SA directly can be reduced, leading to enhanced model capabilities that may even surpass their original performance. Looking ahead, our experiments have shown that using shared attention in the later layers of LLMs results in minimal accuracy loss, making it a viable strategy for improving model efficiency. We also noticed a trend toward more stable attention patterns during the pre-training phase, suggesting that as models process more data, their attention mechanisms become more consistent. This insight leads us to believe that incorporating SA during pre-training could be particularly advantageous, allowing models to adapt better to this streamlined attention mechanism and potentially boosting their performance across various tasks. By embedding SA early on, we might simplify future adaptations and support efficient attention dynamics. Another exciting area for future research is the combination of SA with other attention-sharing techniques, such as cross-layer attention, CLA. Merging SA with methods like CLA could leverage the strengths of both approaches, resulting in a more robust and flexible attention mechanism. This comprehensive approach to managing attention could optimize both computational efficiency and model scalability. By exploring these avenues, we can refine the use of shared attention in LLMs and unlock its full potential to enhance the architectural and operational efficiency of next-generation language models. Our efforts could lead to models that are better equipped to tackle the growing complexity and variety of tasks in natural language processing. In terms of related work, we recognize that efficient memory management in transformers is a crucial research area. This includes goals such as reducing memory bandwidth and storage needs, as well as optimizing computational costs during training and inference. Our focus is on minimizing the size of the inference key value (KV) cache that remains between model passes, which enhances model efficiency without significantly sacrificing performance. We have seen significant efforts aimed at improving the efficiency of the KV cache after training. Techniques like KV cache compression have been widely studied. For instance, methods such as KV-Quant and KIVI use quantization to shrink the memory size of KV pairs to just a few bits. Additionally, approaches like attention sync and scissorhands introduce sparsity into the KV cache by selectively storing elements based on their relevance to the generation token, thereby reducing overall storage needs. Architectural changes aimed at decreasing the KV cache size are essential for enhancing the efficiency of large language models. Strategies such as limiting the effective sequence length, as seen in sparse attention, focus attention on local windows to cut down on both computational demands and memory usage. Another method involves replacing traditional softmax attention with scalable alternatives like linear attention, which maintains a constant space requirement and scales better with the number of tokens. Furthermore, techniques like grouped query attention, GQA, and multi-query attention, MQA, consolidate attention across multiple queries, significantly lowering the memory footprint by sharing KV pairs among attention heads. These innovations are directly relevant to our work and inform our development of the shared attention mechanism, which further optimizes memory usage by sharing attention weights across layers.